Hi, and welcome back to our channel. I'm Boris Dalovsky from Edlitera, and I'm excited to bring you the second part of our two-part series on using the Albumentations library to perform image augmentation. In the first video, we covered the basics of computer vision, the basics of image augmentation, and we focused on pixel-level transformations. In this video, we're going to focus on spatial-level transformations and on building image augmentation pipelines. By the end of this video, you'll be able to create your own image augmentation pipelines, and you'll have a comprehensive understanding of how the Albumentations library can be used to perform a wide variety of image augmentations. As always, we strive to bring you high-quality educational content, and we appreciate your support and feedback as we continue to grow our channel. So, if you found this video helpful, make sure to hit that like button and subscribe to our channel for more high-quality content. And now, without further ado, let's get started. Now that we are done with pixel-level transformations, let's talk about spatial-level transformations. Remember, pixel-level transformations change the values of the pixels themselves. On the other hand, spatial-level transformations change the positions of the pixels in the image. This means that they will change the position, orientation, or shape of objects within an image, but they will preserve their visual features, such as, for example, color or texture. These transformations are essential in creating enriched datasets for computer vision models. However, because of how complex they are, they're not very well suited for all types of computer vision problems. For example, when you're working on a segmentation problem, you need to be very careful about which transformation you're going to apply. And sometimes spatial-level transformations are not really ideal for that particular type of situation. Now, the most popular types of spatial-level transformations are rotation, flipping, cropping, and elastic deformation. Rotation, or image rotation, involves changing the position of pixels by rotating the image around a central point, typically its center. The pixel values are preserved, but their positions are updated based on the specified rotation angle. For instance, a 45-degree clockwise rotation would move each pixel to a new location along a circular path, maintaining the original intensity value of the pixel but changing its position. This transformation exposes models to objects in various orientations, aiding in their ability to generalize across different viewing angles. Then we have flipping. Flipping an image consists of reflecting it along a horizontal or vertical axis. Effectively, we are creating a mirror image. This transformation swaps the positions of pixels while retaining their original values. Horizontal flipping, for example, reverses the order of pixels along the horizontal axis, while vertical flipping does the same along the vertical axis. This type of transformation helps models recognize objects with different orientations or even symmetries and enhances the model's capacity to adapt to diverse conditions. And we have cropping. Image cropping involves removing a portion of the image, usually around its edges, to focus on a specific region of interest. This cropped image retains the original pixel values but has a reduced size. For example, if we have an image that is 200 by 200 pixels in size and we reduce it to an image that is 100 by 100 in size, that would mean that we remove all of the other pixels except for that particular region of interest from the image. So we essentially end up with a smaller image. And finally, we have elastic deformation. All of the aforementioned transformations are relatively safe to use. However, elastic deformation is something you need to be very careful with. Elastic deformation applies smooth, non-linear transformations to an image. Basically, it stretches an image or warps it in a localized manner. This is typically achieved using techniques such as Gaussian smoothing and displacement fields, but the point is that even though the pixel values remain the same, their positions are adjusted according to the generated deformation map. To simplify, let's say that we are applying an elastic deformation to an image of a handwritten digit. This might cause the digit to be slightly bent or twisted, which mimics natural variations in writing styles. This makes sense if you're applying this transformation on something such as an image. But let's say that you're trying to apply the transformation on an MRI scan. Here, this type of transformation does not make sense because you're never going to run into a warped MRI scan. So when you want to perform an elastic transformation, you need to be very careful whether the particular computer vision task you're working on is well suited to those types of transformations, whether you can actually run into a situation when working on a computer vision problem where the data is going to be modified in such a way. Now that you know more about spatial-level transformations, let's demonstrate how we can use the Albumentations library to perform these popular spatial-level transformations. The way we apply spatial-level transformations is identical to the way we apply pixel-level transformation. So we just need to define the transformation itself and apply it to the array that represents an image. This means that we can reuse the augment image function that we defined earlier for pixel-level transformations. The only difference between applying pixel-level transformations and spatial-level transformations is going to be in which transformation we define we want to apply. So in my case, I'm going to demonstrate the most important spatial-level transformations, which are horizontal flipping, vertical flipping, rotation, and cropping. Let's start with horizontal flipping. To apply a horizontal flip to my image, I'm going to access horizontal flipping from the albumentations library. I'm going to store it inside of a variable, and then I'm going to enter it as the first argument to my augment image function. The second argument is, of course, going to be the image I want to apply the transformation on, and I'm going to end up with the following result. So as you can see, this is an image where my golf ball has been flipped. I can do the same thing for vertical flipping. The only difference is that I define that I want to use the vertical flip transformation from the albumentations library, store it inside of the variable right here, and then I apply it using the augment image function on my image. Now, one thing you might notice here is that spatial level transformations are always easy to recognize, even for us humans. So we can always tell the difference between the original image and the transformed image. The reason is very simple. In pixel level transformations, we change the values of the pixels, which can sometimes be hard for humans to recognize. However, because in spatial level transformations, we change the positions of the pixels, even we humans can easily notice the changes. Let's go over the rotation transformation. So the rotation transformation can be applied using rotate from the albumentations library. Again, I store it inside of a variable, and I use the augment image function to apply this transformation on my golf ball image. And I'm going to get a result that looks like this. This is a great example of why sometimes applying spatial level transformations can be tricky. So as you can see, if we rotate our image by a certain angle, we might end up in a situation where we get so-called artifacts. What is an artifact? Well, the artifact is this part of the image that we have right here. The transformation changed the positions of the pixels, and for some reason, we ended up with an extra golf ball image at the bottom left corner. Now, this can be pretty problematic. So this is why you always need to check whether you have defined your transformations correctly. And what do I mean by defining transformations correctly? Well, if you take a look at the crop transformation right here, to be more precise, I'm using the center crop transformation. I'm also defining some values right here. What am I doing? Well, all of these transformations that you can access from the albumentations library actually have arguments of their own. In the case of the center crop transformation, I have the width and height arguments. There are also other arguments you can use for the rotate transformation, for the vertical flip, horizontal flip, even the pixel level transformations that we used earlier. Of course, it's impossible to go over all of the transformations and all of the arguments in this video because the video would be too long. So if you're interested in learning more about the arguments of the specific transformations, I suggest you take a look at the documentation of the albumentations library. In the meantime, I'm going to use the center crop transformation. I'm going to apply it on my golf ball image, and I'm going to end up with a result that looks like this. The center crop transformation is going to go to the middle of the image, and then it's going to crop out a part that's, in this case, 200 pixels wide and that has a height of 200 pixels. This is how I get the result that you can see right here. Now that we went over pixel level transformations and spatial level transformations, the last thing we need to talk about is image augmentation pipelines. Up until now, we mostly talked about how to apply a single transformation to an image. However, in practice, we want to apply multiple transformations. We can do this very easily using the albumentations library, or to be more precise, using the compose function. The compose function from the albumentations library takes in a list as an argument. This list needs to contain different albumentations transformations inside of it. Once we pass that list to the compose function, it's going to build an image augmentation pipeline from it. The image augmentation pipeline is going to apply the transformations that are mentioned in the list, that are the members of the list, in the order in which they appear in the list. So for example, let's say that we have a list that contains the following three transformations in the following order: the random crop transformation, the horizontal flip transformation, and the random brightness contrast transformation. If we pass that as a list to the compose function, it's going to build an image augmentation pipeline. Then what we can do is we can pass an image to that particular pipeline. When the image goes into that pipeline, we are first going to apply the random crop transformation to it, and we're going to get a crop image. Then we're going to apply the horizontal flip transformation on that crop image. And finally, we're going to apply the third transformation, the random brightness contrast transformation, on an image that has already been cropped and horizontally flipped. This is how we can essentially stack multiple transformations on top of each other. Let's demonstrate how we can do this in practice using the albumentations library in Python. Let's demonstrate how we can build an image augmentation pipeline in Python using the albumentations library. But first off, let's explain the concept of probability. I mentioned earlier that I'm going to talk about the P argument of our transformations once we get to these image augmentation pipelines. The P argument is very important because it essentially defines the probability of applying a transformation to an image. Now, why is this important? Well, if the probability of applying a transformation to an image was always 100%, even if we created an image augmentation pipeline of 1,000 transformations, we would still get just one transformed image from one original image. So basically, using image augmentation, we would double the size of our original dataset. However, we can actually do much better. If we set the probability value to a value that's smaller than 1, for example 0.5, which denotes a probability of 50%, then we can get multiple transformed images using the same pipeline from one original image. Now, if you take a look at the example that I have on the screen, you can notice that the random crop transformation will always get applied. However, the other two transformations have a 50% chance of being applied. So when we pass an image through this pipeline, sometimes we will apply all of the transformations on the image. Sometimes we will apply 2 out of the 3 transformations on the image. Sometimes we will maybe apply only one transformation, only the random crop transformation on the image. So as you can see, we actually get multiple results from one original image. In this case, what we actually get is 4 results using 3 transformations from one original image. This means that if we started with a dataset of 1,000 images, we would create 4,000 artificial images, basically increasing the size of our dataset from 1,000 to 5,000 images, which will lead to much better results. The main difference between this function and the function that I created earlier is that in this case, I'm going to apply multiple transformations. The first thing that happens here is we transform our image into an array using the array function from NumPy. So we get an image array. Then I need to create the image augmentation pipeline itself. The way I do it is using the compose function from the albumentations library. To create a pipeline using the compose function, I just need to input a list of transformations to the compose function. And this is something that I'm going to define as my list of augmentations argument. Then I can store that pipeline inside of a variable and I can apply it on my image. I just need to tell the pipeline what is my image, which is in this case the image array that I created right here. And finally, because I get a dictionary as a result, I need to access what is connected to the image key. To get an image from that augmented image array, I'm going to use the fromArray function from the image module of the pill library. So once I define this function, I can actually demonstrate how it works. Let's define a few transformations here. I'm going to pick some of the transformations that we've used throughout this video, and those will be the rotate transformation, horizontal flip transformation, and sharpen transformation. To simulate the example that we had above, I'm going to always apply the rotate transformation, so I will set P to 1, but I will set P to 0.5 for both the horizontal flip and the sharpen transformations. Finally, after I define these 3 transformations, I can put them inside of a list and store that list inside of the transformations to apply a variable. And then what I can do is I can use the augmentation pipeline function that I created. I input my list of transformations to the list of augmentations argument, and I input my golf ball image to the image argument. And I'm going to get a transformed image. And this is how it's going to look like. So this is my transformed image. Now, one thing you might notice here is because we are applying these 2 transformations using P equals 0.5, if I run this multiple times, I'm going to get multiple different results. So as you can see, this result is different from the first result. And if I run it again, I'm again going to get a different result. So there are 4 possible results we can get here because we are applying one transformation with a probability of 100%, and we are applying 2 transformations with a probability of 50%. Let's actually change this to 50% too. So if I change this to 50%, I will sometimes end up with an image that's not even transformed at all. That's the original image, something like this, maybe. So as you can see, using these image augmentation pipelines, we can increase the size of our dataset by a lot, which will in turn make sure that we get better results from our model. That's a wrap on our 2-part series on using the albumentations library to perform image augmentation. I hope you found these videos useful and informative as you explore the exciting world of computer vision. By now, you should have a solid understanding of how to perform both pixel-level transformations and spatial-level transformations, as well as how to build image augmentation pipelines. Don't forget to hit that like button and subscribe to our channel for more high-quality educational content. Thanks again for watching, and see you next time.